Okay, g'day all and welcome to another video. So I thought it might be nice to move along with our neural net program that we were writing. And today what we're going to talk about is activation functions. So the neurons perform an operation in order to accumulate some charge or some value indicating the charge inside the neuron. But we can actually perform some processing on that charge and get a slightly more useful value inside the neuron. Okay, so the functions that we use to perform this processing on the values in the neurons, the function is called an activation function, or sometimes a transfer function as well. Biological neurons don't do this. Biological neurons actually spike. They fire their values in a spike and suddenly shoot out a charge to the surrounding neurons, and then they turn off. There is a little bit of a wobble there as well, but biological neurons are recurrent, so they're all connected to each other in a really complex web. And so this spike in real time can actually lead like wildfire to spread throughout the entire network. Almost entirely different from what we're doing here. But if you want to look into it, there is artificial recurrent neural networks as well. And you can use things like spiking activation functions. Anyway, let's have a little bit of a look at our neural net as it stands. So what we've got is a neural net. This is a big yellow box just here. Our neural net has a training set, which we haven't really looked at the moment, and it's also got a bunch of layers. Now, inside the layers, we've got a bunch of matrices called activations, sums, weights, and biases, and each one of those matrices has a delta as well, or a change, which we're going to use in computing the backprop. Each of the layers is connected to each other. So there's a first layer that's connected to the second layer is connected to the third, but they're also connected backwards as well. So each layer can see its previous and its next layer. So what we actually spent time doing last time, if we have a look at this slide just here, during the feed forward step, what we were getting was this sums matrix. We were computing the sums matrix. And we were doing that by saying that it's equal to the weights of this layer multiplied by the activations of the previous layer. So at the moment, we don't actually have the activations. At the moment, all we've computed is the sums. But what we've got to work towards today is computing the activations from the sums. Okay, so applying the activation function itself is really simple once we have a good activation function. All you're really doing is applying whatever the function is to every element in sums. And that's how you get your activation matrix. It's as simple as that, really. Okay, so why activation functions? We went over this a little bit at the start, but I think the main thing to keep in mind is that they work. A lot of the stuff in artificial neural networks is really used just because it works. And nobody is actually aware at the moment, as far as I know, of the best way to do a lot of this stuff. We use these things because it works. And the field is really wide open for anybody to jump in with really good ideas and mechanisms and really shake things up and change things. That's really the fun of it, just exploring and testing things out yourself. So for one thing, activation functions are cool because they could allow us to set a range on our values. So instead of having neurons that can range up to 150 billion all the way down to negative 150 billion or whatever, we can actually lock our neurons to a range, say 0 to 1, and that's really useful for computing binary things, which is obviously important in computing. Okay, so they soften the logic. This is really interesting. So if you think about something like a Boolean system or a purely logical yes, no, a black and white system like Boolean algebra, it's brittle in the sense that you might be very close to the correct answer, and then you could just perform a single operation, say not on your result, and suddenly you're nowhere near the correct answer. So it's really brittle in that small changes in a Boolean expression can have vast effects on the output. So one of the ideas of the activation function is to kind of bring that into the domain of real numbers and try and soften the logic a bit. Just make it so that it's not quite so brittle, so that we don't accidentally flip one little switch and suddenly we get everything wrong. Yeah, we want to be able to approach the correct answer or a correct answer rather than just have things yes or no, so black and white as Boolean systems do. So one of the important things that an activation function does is allows us that freedom to make things less brittle. It also gives us a first derivative. Yeah, so if you're working with Boolean systems or black and white systems, there's often not going to be derivatives. Your function might not be continuous. Yeah, so activation functions give us that first derivative, which, as we'll see later, allows us to do backprop. Okay, so the logistic function is an old activation function. It's still in common use today, and it's a sigmoid. I love this. It's called a sigmoid because it looks like an S. Just classic. Yeah, so that's the graph just there, and what you'll see at x equals 0, the value of y, or the value of the logistic function is 0.5. Yeah, and you'll see that as you get larger and larger x values, say all the way up to 10, then the logistic function actually approaches, but it never quite gets to the return value of 1. With very large negative values is very close to 0, and then as you approach 0 with your input, your x value, the sigmoid suddenly has this curve, this S-shaped curve that gives it its name, sigmoid. And then with very large positive values, the sigmoid function return value will approach 1. Yeah, so we get a range just there of 0 all the way up to 1. Yeah, and it reduces the chaotic output of binary. Yeah, as we were just saying before. So the sigmoid softens the logic a little bit for us. So that's really, really nice. This is the sigmoid function down here, as we will put it in code in a minute. It's 1 over 1 plus e to the power of negative x. That e is that magical e constant. We'll have a look at Wikipedia. Which is where I got these pictures, incidentally. Yeah. So the first derivative of the logistic function is down here. This is f of x, which is the logistic function itself. So it's the f of x multiplied by 1 minus the f of x. It's used for outputs. Yeah, as we'll see later on, it's usually used for outputs. It's sticky. Yeah, so one of the problems with the sigmoid function, this goes for the logistic function and tanh, which we'll have a look at in just a second, is that it's sticky in the sense that if your value is very high, say it's 100 or something, then the sigmoid function will be very flat at that point. In other words, the derivative or the change, which is what the derivative represents, the change will be almost 0. And so your neurons won't really move from generation to generation. So this is a real problem with the logistic function and also the tanh. Whenever you've got very large positive values or very large negative values in terms of magnitude, your sigmoid's derivative is going to be almost 0, especially when that's tied to the rounding of floating points. What you'll find is that your neurons won't really move from generation to generation, and they can kind of become locked at certain values, and they're not able to change because the first derivative is pretty much returning 0, or indeed it might be returning 0, especially if you've got your denormals set to flush to 0. Okay, so the next activation function that we're going to look at is called tanh, or the hyperbolic tangent, and this is very, very similar to the sigmoid function, or very similar to the logistic function, sorry, that we saw last slide, except that the range is slightly different. I think it's also slightly steeper. Yeah, so where the logistic function returned a value in a range of 0 to 1, the tanh function returns a value in the range -1 to 1. Yeah, so that might be useful as well. If you're dealing with binary, you could say something like -1 indicates not or off or 0, and +1 indicates 1. So very similar to the logistic function from the previous slide, only it slopes more and it has a larger range. This is the computation down here. So it's e, once again, e to the power x minus e to the negative x, etc., etc. Yeah, but just like the logistic function, the tanh function actually suffers from much the same locking problem. We might actually end up with neurons that are kind of locked and stagnate in one single place, and they're not able to move because the derivative isn't moving. Okay, ReLU. So ReLU, or the rectified linear unit. I don't know why they called it this. It's just a very funny name. With a lowercase e too, ReLU. Anyway, rectified linear unit is really, really simple. It's the maximum of 0 and x. Yeah, so if you input the value 10, then ReLU will give you 10. If you input the value -10, ReLU will give you 0. Yeah, it's as simple as that. It doesn't saturate y. There's no limit to what y can be. So If you input 150 billion, then you're going to get 150 billion back from ReLU. And the other thing about it is that it's not continuous. So these are the functions down here. F of x, if it's 0, then, or if it's less than 0 or 0, then return 0, otherwise return x. And the derivative for it is really, really easy. The derivative for it is 0 if it's a negative number, or 1 if it's positive. Okay, so a lot of the things that we're teaching here actually came from Andrew Ng's Coursera course. I'm not sponsored at all, but I did take that course and I found that absolutely excellent. All right, so the strategy he recommended was ReLU for the inner layers, which allows fast learning and infinite gradations of importance. And it also reduces the ability for neurons to accidentally lock to particular values like the sigmoids did. But for the final layer, we use something like the logistic function or tanh, so that we can set our output to some range, say -1 to 1 or whatever. Yeah, okay, so that's just about it. I think we should get to coding. Okay, let's have a bit of a look. Okay, so here's our little program just here. And if we come over here to the to-do list, the first thing that I'm going to do is add an activations.h function header to store the functions. And we're going to add those 3 functions so you can have a bit of a play around. The other thing that I want to mention is if you come over to Wikipedia, I might leave a link to this down below. This is actually Wikipedia's activation function page. And if you scroll down just a little bit, you'll see a list of all of these activation functions, a whole lot more than what we're going through today. And really, the only limits to the activation functions that you could implement, the only limit is really your own imagination. How wonderful for us all. Alrighty, so what I might do, I'll just right click on this little fella and we'll go add new item. I'll come to header and we'll call it activation functions. We'll add those 3 along with their derivatives. Okay, so the first thing that we might do is just include IO stream in case we've got to print something out, and also for the power function, weirdly enough. All right, so float, we'll call it logistic function, and it's float x. Okay, and the logistic function is logistic, soft step, 1 divided by 1 plus e to the power of -x. Alrighty, 1.0 divided by, let's have a bit of brackets, 1.0 plus pow e to the -x. And let's close those brackets and let's return. So those are floats. And e, we better define e. So this is the mathematical constant e, which I'll also get from Wikipedia. E, the mathematical constant himself or herself, whatever happens to be the, I'll copy that. One of the most interesting numbers out there, I reckon, though there is a paradox on just how interesting numbers can be. And define E. So that is the logistic function. And now we'll say the logistic function derivative. We also need the derivative, so float f. I might call it x again, actually. Okay, we'll see if I can do this from memory. I've done this so many times. Logistic function x multiplied by 1.0 f minus the logistic function x. I think that's the derivative. Let's have a bit of a look. Return. Yeah, there it is there. So the equations you'll find just here on the Wikipedia page, and the column beside that is the derivatives of the equation. So the derivative of the f of x with the logistic function being the f of x himself is f of x multiplied by 1 minus the f of x. Good stuff. And the next one that we might do, might just add, just in case people want to play around, is tan h, or the hyperbolic tangent. Float x. Okay, well, there's actually a maths function that does this. So you could... where is it? You could type this out if you wanted to. It's here, this one here. E to the power x minus e to the negative x divided by e to the x, blah, 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 blah. But I'll just call the maths function. I don't know if it's cross-platform. Yeah, you might have to include math.h or something like that if you're working with Linux. But return tan h of x. Float. Okay, and the derivative of tan h, whoops, I cannot remember this. Let's see, we'll just give that a bit of a save and we'll come over here. The derivative is 1 minus the tan h of x squared. Alrighty, so 1.0f minus tan h of x times tan h of x. Return that. Alrighty, so there we've got the two sigmoid functions defined in case we want to use those in our program. So the way that we're going to set this up, I'll make it so that it's fairly easy to use any one of the activation functions and to change it pretty much whenever you feel like. I think that's the best way to play around. All right, but that's the two sigmoid functions. So the other one that we need is ReLU. So float ReLU float x, and we'll just say if x is less than 0.0f, return 0.0f, otherwise return x. So the derivative of ReLU is possibly even easier. Now I'll just copy this, might zoom in a bit. All right, so if x is negative, then the derivative of ReLU is 0.0, otherwise the derivative is 1.0f. There is something called leaky ReLU as well, which is really worth looking at, and I think maybe even more popular than ReLU at the moment, I don't know. Anyway, that's our three functions defined in our little activation functions header. So now what we've got to do is add a function to our matrix class, and I'm going to do this with a function pointer. I don't know if this is the best way to do it, but it's certainly one way to do it, so that's what I'm going to do. Add apply function to our matrices. All right, so we want to be able to apply these activation functions to our matrix class in order that we can compute the activations matrix from the sums matrix. So what I might do is say void. This is in my matrix.h class. I'll say void apply function, and it's going to take a function pointer. No, it's going to take a matrix, I think. Matrix star dest, the destination matrix, and it's also got to take a pointer, a function pointer to the activation function that we want to use. So it's going to be float star function and float. Yeah, something like that. Okay, and then all we've got to do is say for int I equals 0, well I is less than total I plus plus, and we want to say dest data I equals whatever the function is applied to data I. Yeah, so that's all that does, just applies some function to every element in this matrix and stores it in dest. All right, we'll give that a bit of a save. We'll come over here. All right, set the activation functions in neuralnet.addLayer. We want to use a sigmoid for our final layer. So what we can say here, after we've pushed a layer onto the back of our layers vector, we can say layers dot back dot set activation function, and it's going to be ReLU. Okay, so I haven't done this in a very good order. Yeah, we want the final layer to not be ReLU actually, so let's do logistic function instead of ReLU. And if it's not the final layer, so whatever was the final layer before we've done this push back just here, we might do it up here, I think. So whatever's at the back at the moment, dot back set activation function. Okay, so this method's not actually written yet. That's why the thing is complaining about absolutely everything. ReLU. Okay, so when we add a layer, we set the previous layer, the previously added layer, if it exists, we set the activation function to ReLU. And we might also say up here, ReLU derivative. So whatever this set activation function is, it's going to take two parameters, the activation function and the derivative. And we'll go here, logistic function derivative. Yeah, so if you want to play around with 10H or any of the other activation functions later on, then you can just put them in the header and switch these little values just here. What I might do first is I'll scroll to the top and get rid of some of those errors by including activation functions.h. We'll scroll back down again. Okay, ReLU derivative doesn't exist. Well, what is it called? Did I not make it? Oh, I called them both ReLU. Problem solved. All right, so now we'll just save that and we'll go to our layers function and we'll add two function pointers, one for the activations and one for the derivative of the activations. And we'll also specify this function just here, set activation function, over here to layers. Okay, void set activation function. I keep making that F lowercase. I don't know, my pinky's getting lazy. Wake up, Russ. Alrighty. Float star activation function float, and the other one that we need is float star deriv and float. Okay, so I might say activation function or this dot activation function equals that. And we'll say this derivative okay, and we'll come to the top and we'll define those as member variables. It's going to be float star that thing, and I might just copy and derivative. Is that what I called it? Derivative? Yeah. Okay, so that's allowed us to add layers, and when we're adding the layers, we're setting which activation functions to use, be they sigmoid or ReLU for the inner layers. So the final thing that we've got to do just here is call the activation functions when the layers feed forward, so that we are actually computing the activation matrices instead of just the sums. All right, so last time we left ourselves a nice little message, perform the activation function. All right, let's do that then. How though? Sums, apply function, and the destination is activations matrix, and the function that we want to apply is the activation function. Hit run and see what's happening. See if we've got errors. Yeah, we do have errors. Let's have a look what our error is. All sorts of warnings that nothing's initialized. Well done, ya. Must have a struct or a union. Set activation function. What are you talking about? Why must it? What? Oh, sorry. They're pointers, yeah. Hail to all of the people that told me not to use so many pointers. You might be onto something. Everything's a pointer or a reference, and then you start to lose the plot. Not to say that I ever had the plot. Okay, it all seems to be running reasonably well. So if we come over to our main, just here, after we've added our layers, what we might try and do is feed forward or forward prop and see what happens. Just as a little test. Okay, so exception, char at memory location that. Well, what does that even... Okay, so it took me about 50 years to figure it out, but that should be if the layer size is less than or equal to 0. I think it should be if the layer size is less than or equal to 1. So if there's not enough layers to feed forward, then we obviously can't feed forward. Let's just hit run again. Okay, so another little bug just here. If there is no previous layer, then this layer here that we're feeding forward is actually the input layer. So we don't want to perform these first few operations. So we'll say if previous layer equals, is it null PTR? does not equal null PTR. Oops. And we'll do that stuff. Otherwise we can't feed forwards. Just a little bit of bug fixing. This was a null pointer. How? So I'm guessing this error just here, this was a null pointer. I'm guessing this is because destination is set up, but the data for the input layer is not set up, since the sums don't exist for the input layer. So what I might just do is make sure that we're not calling apply function when our layer is the input layer, which is this one down here. So if, once again, if previous layer does not equal null PTR, I'll just put that comment out there and we'll cross our fingers and run again. Let's see how we go. Okay, yeah, we got through the run with no problems, excepting the 12 times that it wouldn't compile. We had no problems at all. Okay, sorry about that. My camera cut out. It just cuts out at random times. I think it's got like a 4 gig limit or something like that. But anyway, we're back again, and I just want to say thank you very much for watching. I'm going to put the source code and slides up for the Patreons, just as a big thank you for supporting this channel, and official merch down below if you want to get yourself a What's a Creel t-shirt or a coffee mug or something like that. Yeah, there'll be a link to a storefront down below from Teespring. Other than that, thank you very much for watching. Have a good one. Adios.